Okay,
Am I,
yes.
Second here.
Yeah.
okay. All right, okay, so my talk is about. Am I in the way?
Do this. I don't know how to
Right, this is
no,
off.
my mouse doesn't, it's not visible when we are off, on full screen. Okay.
The slide's a little bit cut off.
Yeah, that's a problem with the screen,
That's
Oh, okay.
unfortunately.
They
Right,
can
I'll-
see it.
I'll lose talk, so. People can hear me. Hi, I'm Anne from Carnegie Mellon. Yeah, so my talk is about how to bridge classical statistics with, where's the camera from below? With machine learning and Bayesian ideas for reliable, trustworthy scientific inference. Okay, so here's a schematic of the interplay between theory and data. So given a theory, you can make predictions on the data, and given data, you can make inferences or constrain or test your theory. So I refer to the prediction problem as the forward problem. And what we're interested in this talk is the inference or inverse problem. So the direction is important, it's not symmetric. Okay, so in many sort of complex, for many complex phenomena, the theory is often in the form of simulations. So you can think of your physics-based simulator as a causal model that encodes the data generating process. Can you see if I point with my hand? From the underlying parameters of interest to your observable data. So the direction again is important. It goes from the data generating process goes from theta to your data. And the question is, how do we test or constrain our theory given data? So you can imagine here that we have two settings. So one is that we have a simulator that implicitly encoding our data generating process of likelihood. So in this case, I can generate a labeled set for different parameter settings data. And if I have my model, I can generate observable data for that data. So you can get labeled data set. And another setting is we actually don't have simulator. Nature is the simulator. It could be an observational study where we have partial label data. So we might have precise labels for subset of the data from auxiliary measurements. So an example is, for example, in photometric studies, you might have access to spectroscopic labels of high precision for subset of the data. So in both cases, we can think of it as access to label data for some of the data, so pairs of parameters of interest and your observable data. And from that, we want to infer the internal parameters or measures of uncertainty. And you've probably seen like some pictures like this where you have region estimates. So this is for cosmological parameters. These region estimates for, you have different constraining power for different surveys. And the question is like, are these, can we trust these? Are we confident that these regions actually include the true unknown parameter with high probability? Can we say, with, for example, 90% confidence, these region estimates would include the true unknown parameter, which we don't need, right? And do these sizes, are they actually meaningful? Do they reflect our constraining power? Like how well we can sort of estimate our parameters of interest. So I'm actually looking at problems where different project applications where we estimate what I would call local parameters of interest. So what it means is that I have a different parameter for each measurement. So it's not like a cosmological analysis, the typical statistical setting where you have the same parameter for all the data. It caused some confusion with my stats colleagues, so I'm spending some time on some examples. So one project I've been working on is, the goal is to measure the energy of a subatomic particle from calorimetric data. So the data will be the energy deposits in a highly granular calorimeter.
So just to clarify, so you mean local as opposed to population? characteristic.
It means that I only have one observation, then I want to know energy of that particle and I want measurement. So I can't do repeated measurements. That's what I mean with local. So it's not global parameter for the entire population.
Whereas if you have a whole bunch of
Yes.
photons together, you might be able to measure the temperature of the plasma that it's.
Yes, so, but let me, okay, so here's maybe closer to what you guys do. So here's another like simulation-based inference problem. Where we want to identify, well, first we want to separate gamma ray showers from hydro showers. And this is a simulation. And we'll have ground-based Cherenkov detectors. We want to identify the gamma ray showers and then reconstruct the showers. So basically estimate its orientation and energy. And this is simulation. So for each gamma ray shower, we have sort of one measurement of the secondary particles, like the counts in this array. And the other that I'm working on now is, you want to estimate the properties of stars from, for example, this spectra. There's nothing in the images, right? So, and this would be what I mean with local. So you have one parameter of interest. So for example, the mass, age, composition of the star, and I have one spectra. So I don't have repeated measurements of the same thing, it's from survey data. So it's local, meaning that it's not like many measurements. So sample size for statistician will be one, and that's confusing. It doesn't make it clear.
Yeah.
I think so. And so we think of it, that data coming from Jones, so from the likelihood, and then what I call the prior, which just means the distribution of the theta. Okay, so it's not the typical statistical setting. So the thing is that sort of the complex scientific inference is often likelihood free. And what I mean with that is that, you know, if you know the likelihood, right? So the likelihood basically connects the underlying parameters that you observe with data. And if I know the likelihood and I can evaluate it, then I can use standard, whatever, frequency Bayesian ideas. I can use numerical methods such as MCMC. Okay, so the likelihood, as I think of it, is you have the nature, the data that are present, the physics, and then the observational effects, which are not negligible. But this is the likelihood, right? So, but often in many cases, you don't have access, you might have it access through sort of nature, the simulator, but you can't evaluate it. And like in high energy physics, it might be intractable because you have all these integrals, you have latent variables, but you can't do the forward simulation. Or if you have a nature, I can measure the sort of the label data thetas and the x's. So that the inference problem is much harder, I think. I also work on the prediction problem, but I think inference is really hard, even if you have the forward model. And then maybe the forward model is no good, that's another issue. So the assumptions, you have to make some assumptions to do this. Or I should also say the likelihood free inference, the term I use, or LFI for short, means inference in this setting. So likelihood free inference does not mean that you don't have the likelihood. It just means that I can't evaluate it. I might have a model, or maybe I don't have a model. I have the nature that's my simulator, but I can't evaluate it. So I can't use MCMC, for example. Or another situation might be, maybe I can use MCMC, but it's just not, it's too slow. Like I can't apply it to big future surveys with millions or billions of galaxies. It's also a computational issue, right? So you can bake that together into LFI if you want.
So free is really the opposite of what you said, is too costly.
Yeah, some people use for the term implicit likelihood. I mean, there's terms like matrix free for these input output. It's not that you don't have the matrix, it's just like I can't work with it. It just means intractable. So whatever, like it's historical reasons. And so there has to be some assumptions. So the assumptions I have in the framework I will show is that the likelihood does not change between training and inference. So there's no unaccounted for model uncertainties. So you do inference is done on the model or whatever, right? You assume it's the same. But what I call the prior, which is how we observe my trained data across the parameter space, could be poorly designed. And I think I need to spend some time explaining what I mean with prior, because it's not a prior in a strictly Bayesian sense. Okay, so this is kind of a machine learning friendly setting. So I have a train set of the pairs of parameter interest and observable data. And then I have a target set where I have the observations and I don't know what the true parameters are. Okay, so what is the prior? Okay, so the likelihood is the data and process, so the physics plus observation effects. And the prior with I just mean that is the distribution of theta in your label set. So if it's a simulation depends on how I simulated it. But if you observe it, then as astronomers, it's whatever I observe in your set. And that may not be the same as the distribution of theta in my target set, because I don't see everything. Or if you're Bayesian, maybe when I simulate, I don't really know, and it's the belief. So whatever it is, once I put in this setting, I think it's clear what I mean with distribution of theta. It's whatever I have, what I train, and I'm going to use machine learning method for whatever I train here. So if you use posterior or whatever, then you know that the posterior by definition depends on both your likelihood, which I imagine is the data and process, and also whatever you call it here, the prior. So whatever your credible regions, of course, will depend on both. And there's an issue, and I will show you, and this is not new stats, that if your prior is mismatched with the target one, then your inference from your posterior credible regions might be misleading. I mean, it's a known problem. So when I say misspecified mismatch, it just means I assume that likelihood is the same. I have to assume something. But I have a distribution difference. The prior may not be the same as the target because of various effects. Is that kind of clear? Yeah.
I think I get it, but I think it will help
Yeah, and you
some
can.
the students to, if you give an example, what I
Yes.
want
I
to
will.
know here is, in a general kind of prior likelihood formulation, we have an implicit notion that if the data can be accumulated without limits, eventually I can narrow down what
Yeah,
the CETA is. Is
yes.
that possible here? What are the
No.
CETAs here?
Yes, it's true, but I don't use asymptotic, so whatever.
No, I understand that. I
Yes.
just conceptually to understand what the CETA means here.
Oh, what theta means?
Yeah.
Theta is my internal parameter of interest, so it's what I think is true. So I will show examples of stars. I want its properties, its mass, its composition. I don't think of it as random. If you want,
No,
you
that's
can-
fine.
yeah.
That's fine. So you're
That is
saying,
theta,
okay.
but there's a different one for each observation.
Okay,
That's the
got it.
key.
got it.
And
But
so you cannot use classical frequencies, large sample theory.
that's
Yes.
entirely fine. But what are you trying to infer? You're gonna infer the distribution of CETA.
No, I want to form confidence sets of the theta.
Which one? Because each one has its own CETA.
Yes, each one I form a confidence set, and my claim is I can do it with sample size 1. And this is
Okay,
new.
so you wanted to, yes, okay, so you're inferring, you want to infer, it's like an individual prediction.
Yes.
You want to
Yes,
each individual.
Because I
Because
don't
you-
care about
Okay, got it.
the whole
Fine.
survey, right? I care about that star, that galaxy, that subatomic particle, then it's gone.
But because you have a model to connect all these
I
similarities.
need a model. The only key is that this has to be the same.
Yeah.
That you can have a model or you cannot have a model. It can be implicit in your data. That has to be the same. And this can be different. But I don't think anyone is working on it. But it's very easy, the solution. So with sample size 1, right? You can do it.
Sure. You mentioned the asymptotics thing, that like
Yes.
in a Bayesian sense, if you have a.
Yes, but you
an
can't,
infinite limit of
yeah, you
data-
can't do, there's no,
Yeah,
sample
No.
size is 1.
Yeah, but I'm saying like,
Yes.
in the limit that, because at least when I read about like pre-inference, usually in practice, you like train a neural network to like learn the.
Yeah, it's wrong. No, it's wrong. I'm out of time on it, so.
Yeah, I think it's just a very quick concept issue. For the given CETA, for the individual, if for the same CETA, you can have lots of
Yeah, that is
observations.
so easy.
That's an easy problem. I understand that, but conceptually, that's the CETA you are trying to infer. Because if every observation, every time at a different CETA, you can't really infer that particular.
But you
CETA.
can. But you can't, because let's just take the simulation,
right,
so do not
right.
care about that, you can't. Why can you not? Do you know the forward process here? So let's just do simulation because it's easier to understand. If I know the forward process, I know I have an all-knowing simulator, so that's where I did high energy physics. If I know an all-knowing, then if I observe X, I should be able to infer theta with measure a confidence set. I should.
If you
Because
have
I
a
have an
model.
all-knowing simulator, why can't I go back? But I'm not
I
saying it's
understand.
easy, right?
No, I understand.
Yeah, so let's do that problem first. So it's not like if I don't know anything, yeah, you can't do anything. But if I have an all-knowing data gen process, if I know this,
Yeah,
but I
I see.
can't yes, then that is the key. See,
But
there's-
that's actually purely Bayesian.
No, there's nothing Bayesian. I have to continue. Yeah, there's nothing Bayesian here. Yes, every single approach I've seen
Yeah.
has been Bayesian, but you can do frequentist incorporating Bayesian ideas.
Yeah.
Right?
Okay,
So
well, we
it's
can,
very simple.
we can
Yeah,
talk.
it's very simple.
Yeah.
It's just like the connection took time and then I just, okay, so
Can
first.
can I just say, somebody should be watching the hands-on learning. Jeff had his hand up for a long time.
Oh, don't, yes, just speak up, please. Whoever has a hand up.
Yeah,
Jeff, yeah,
Jeff.
please.
Sorry, I'm a little, I can't hear the comments in the room too clearly, but I just want to be sure I understand this likelihood-free concept. Is it fair to say that what you really mean is that there's no exact analytic formula for the likelihood, and you're
Yes.
instead using an empirical likelihood?
I haven't talked about the solution yet.
Yeah, you don't-
I'm just saying that, let's just not talk about observational studies because that's a step away. Let's just say that I can simulate for any theta, I can simulate X perfectly. Let's just do it easy. Likelihood-free means I can evaluate this. So if you do MCMC, you for different theta and X's, I can get a number for this, the likelihood. I cannot do that because there are these integrals and whatever. Let's just make it simple. But if you look up likelihood-free inference, you're just going to get A, B, C, and other stuff in the literature. But that's, as I see it, that's just approach, algorithm. It's not, this is just a setting. I haven't talked about the solution. Is that
Right.
Good?
Yeah, maybe I should wait until the end, but just quickly, why do you say the inverse problem is hard? Isn't it with an empirical likelihood? Isn't it straightforward? It's numerical, but it's.
And
why
you
is it
want,
hard?
I haven't, you want a confidence set that has the right frequentist properties guarantees that, yes, it's not, it's hard to do it.
Okay.
And
Sorry
I'm
to-
not getting point estimate. I want to have valid, actually, yeah, okay. Let me continue. Otherwise, I'm really not getting very far. So, okay, so here's the thing. So usually when people have a labeled set and you're interested in your theta and you have X and it's very complicated. So it's like images. These are 50,000 dimensional. You have sequence image, I work with satellite, a hurricane. And if you want to infer this, then maybe you say that's low dimensional. Maybe it's not, it's less than 10, maybe it's 1. In this case, energy is just a scalar. So almost all I see from what you do in machine learning and scientists do is they try to predict it. They use a neural network to stick in this high dimensional thing to predict it, or they form like posteriors because you have these tools, you have the general models, your neural dense system, and then you compute your posterior, which depends on both likelihood, and I claim the prior could be biased. And then they look at the highest density region, or whatever you call it, the form credible region, they think that the truth is there. But it may not be, and this is known, right? So let's just give some concrete example. This is just to show that the predictive approach can be very powerful, but one needs to correct for bias. So this is the original problem I was working on. You have a subatomic particle, a muon, entering a. This is a simulation. It's costly to build this. So it's a highly granular calorimeter, 50,000 cells. You measure the energy deposits in these. And from the simulations, in this case, we have the pretty fast. So it might have like or 100,000 or 500,000 simulations. But the thing is that what we want to measure is the energy of the neuron or its momentum. And we have one measurement, the calorimetric in 50,000 cells. So then there's a new energy one and another one. So it's really sample size. You can think of sample size one. And the natural way, since I'm interested in scalar quantity, and it's cut off here, so you can't see my equations. The natural thing is that you try to predict it. What you do, you try to predict your theta given x's, which you can't see here. And when you do that, it's going to be off. So I know the truth because it's simulation. So this is the true energy for all these 500,000 neurons, and this is the predicted one. And your predictions, you have this bias, a high energy, which is actually the region we're interested in, and you can try to correct for it. But really, what you do when you predict is you're estimating the posterior mean, right? And that's not the same as the underlying true theta, because it's an inverse problem. It's not a prediction problem. So you can try to correct it, and this is typical people do that. They have some prediction to change the loss function, but it's a foundational issue. And here's a similar thing that is also cut off. Posteriors do not guarantee coverage in internal parameters. They're often overconfident. Here's a paper from Jill Loop's group where they discuss that they try different algorithms. There are different neural posterior estimators. They might produce, they're shown to produce overconfident posterior approximation, which makes them demonstrably unreliable, dangerous if one scientific goal is to constrain parameters of interest. Okay, so let me just show you a textbook example. And this is kind of for Kessler-Berger. It's cut off here.
We can actually see down.
Yeah, but not axis. I can explain. So the likelihood, you can do it analytically. So the likelihood is just like, let's say normal likelihood. I can do pen and pencil. I know the mean. I don't know the mean. That's my parameter of interest. I know the variance, and I can put a prior on my parameter of interest. So let's say I do the normal conjugate prior. Let's say I center at 0, and you can compute credible regions. Let's say 95 credible regions from, the posterior is easy. And it's normally distributed. I form a 95% credible set. Now let's see if it actually includes the true theta. And this shows you the coverage, and on the x-axis you have theta for different regions. And if theta is 0, then your credible region its coverage will overcover a little bit. It will be pretty close. So if your prior is matched with the truth, it's not bad. But if the prior, which is at 0, and the true value is far from 0, I can't see the axis, then you undercover, and it can be like 0 coverage. This is just Kessler-Berger, intermediate stats. And basically, if your prior, and you wouldn't know, if your prior is not matched with the truth, then you cannot believe your credible regions, right? And I can do an example, which I can't do analytically. And this is just like I fit the neural density estimate. It doesn't matter what algorithm you do. It's just a 2-dimensional example where 2 normal, I don't know the mean, the variance is different, I know the variances. And the red star is the truth, some example credible regions. This is the coverage diagnostics, which can get from a method. It's basically the same thing. So I put my prior here in the center. So if the truth is in the center, my coverage is about right. It's overcovered a little bit. So I think I want the 90% confidence region. So these are credible regions. But if the truth is far away from where you put the prior, you can compute your credible regions, but the coverage is, I think it's like 30%. It looks good, but it's not, it's kind of, I think it's a little bit misleading. And there's an easy solution for it that's computation very efficient. But doesn't make sense. I'm speaking a little bit fast now. Okay, so I think this is what the overconfidence is. You can compute, you can use a neural density estimator. It doesn't matter what tool you have. It's just what happens. So what does this mean for reliable scientific inference is the way we can still take advantage of neural posteriors, posteriors, but it's neural because your inputs are images and whatever. So that's the big tool you can use. Generative models, those are just like techniques to me. And you know, AI has made real breakthroughs, but can you actually use posterior to do, you know, actually reliable inference? And these are sort of what we want to do. And what we've done, we basically developed LFI procedures with the following properties. So you have robust coverage guarantees. So these are frequency coverage guarantees with 90% confidence, whatever you want, under poorly specified price or shifting price. But then we want, and this CHASC statistic doesn't give you that. We want tail constraints when the price is consistent with your data. And I've been working on this for a long time. I want validity, actually the nominal coverage for all theta. So not just marginally, because as you know, if you want to estimate the properties of star, you care about that star, not like over the entire Milky Way or the universe, right? I'm interested in valid confidence sets locally for every theta. And this is a big thing. And I think that's what people use frequent statistics, the scientists. I want this to be true in finite samples, even if I just have single observation, because as you know, in theory, I can repeatedly make measurements of the same star or galaxy, but you have the survey data and you have that image or that spectra or whatever. And in high energy physics, it's even worse, like your product comes and then it's gone. I cannot do multiple measurements, right? And then the last, and I worked on this for 5-10 years, we also want interpret diagnosis that actually checks the coverage across the entire parameter space. Regardless, if you put your credible region, whatever method you have, I can check where in parameter space I'll get my frequency coverage, where I don't. So even if you don't like any of that, you can use your credible regions and see how good it is. So this is what we want. And in formalized, we'll basically, it's a very simple way of bridging advances L5 with basically old 1900 statistics to leverage AI methods, or whatever you call it, to construct these sets. You have confidence sets that are actually cover includes the true parameter, and it's not Bayesian. I'm not Bayesian because I consider that there's a truth. It's not random. This is random, but the probability of doing this is your nominal 90% of whatever you pre-specify, and this is kind of important though. So I want coverage. I want local validity for every single object in my population, not globally, and this is the thing. I want high constraining power. If I have good price, whatever, this means that this is my likelihood. For each data, I have a model for D, or that it's built in, but my distribution might be different. So I want high constraint power. You have average power, average size when I average over the target distribution should be small when I have good prior information. That I can check, except for theoretically. So this, does this make sense?
Yeah.
Okay, yeah.
Question.
Yes,
Is your capital data here the
this one,
yeah,
it's my
that the
parameter
training-
space,
is that that the training data is taken from, or the
both,
for both?
yes. Oh, well, I guess I'm most interested in target, right? So I get, yeah.
But that
Yeah.
should be part of the training.
Yes,
Otherwise, you
yeah.
won't get it.
Yes, exactly.
It's
So it's, yes,
Can I ask a silly question? So you have that expectation of RD.
Yes.
RD. What does that mean?
yeah, so I'm frequentist, so the randomness comes from the data. This is a expectation of average of all the data in my target.
the expectable.
Yes,
Oh, but then you have a different theta for every data set.
yeah, but the theta is fixed, right? Yes,
That
exactly,
the procedure
yes,
moves, so you can talk about.
Oh,
it.
yeah,
okay.
yes,
So that's a frequent
yeah,
disadvantage.
yeah, so that's yeah, exactly what you said. So the average is with PD.
Yeah.
And and it's the PD of the target that, but which I don't know, so, yes. Okay, so can we have it all? So again, to review, so I want valid inference for small sample size, such as sample size 1, which is poorly specified prior, higher constraining power, well specified. I think SAS people, I'm not for statistics, they already know this. It's just that we have an implementation. That is the difference. And we want diagnosis across the entire parameters, so we can actually check, do we actually get the right coverage? And yes, the answer is yes, it can all be done by leveraging existing posterior or ML predictive tools as is. I think that's computational. But I think our contributions that we actually can do this, we have the software and the all model procedures that have theoretical guarantees. Okay, so the general inference machine, I've been working with my students, Nick, for maybe 5 years now. The paper finally accepted in EJS. We have an early ICML paper from 2021. And we call the framework likelihood-free frequentist inference, so LF2I. And it's very simple idea. So it's not, it's from 1930, I would say. So yes, at some point I have to talk about astronomy and sheets notes and so no, but you can help me. So now I'm fine. So okay, so you got cut off maybe. So our method is really based on the equivalence of test and confidence sets. So you've probably seen that as maybe undergrad at some point, but hey, I ignored it. So you can build let's say 90% confidence set. It's the same as hypothesis testing. So for every theta 0 in your parameter space, you basically test it at level 0.1 if you have 90%. And then you see whether you reject or not. And your confidence set will be the set of all the thetas that you test, theta 0, that are not rejected at level 0.1. I can show you slides for that. So in keywords, you have to have data. You have to have a test statistic. It could be the likelihood ratio test statistic. And you also need to know the critical value, right? For when you should reject. And should I skip this maybe?
No, you have time, don't worry about it. Keep it.
It's just to remind people what the name and version is and why people haven't done that and why you cannot ignore it because it's just computational. It's a computational hurdle. So, I mean, in theory, it would be like this. So everything that we're not doing this, but everything on your parameter space, you have to find the critical value for which you reject at level, this tail, you have 10% probability of being that. You have to find that cutoff, right? I'm sure you heard that at some point. And for that data, let's say this is the acceptance region, accept in that region, and I have some test statistics on conformity score, whatever you call it, and then I reject here. And the problem is that you would have to, you have a different, well, the test statistic would depend on data, but you also have different cutoffs for each data, and these are the acceptance regions, right? So it's like, how would you get it? I mean, in one dimension, maybe you could do bootstrap or Monte Carlo, but your parameter space is not one dimensional. And then let's say I observe my test like I evaluate it, and this solid line just shows when my test statistic in the acceptance region. So it's just to remind you what Neumann confidence set is. So the confidence set is kind of like all the narrow sum Bayesian, but you can't be more frequent distant than the Neumann confidence set. So it's all the thetas that are not rejected. So every time you're in the acceptance region, the set of that is a 90% confidence set if alpha is 10 and 10%. Okay, so the thing is that this sounds like impossible to do computational, which is why you don't do it. So the challenge to computing frequency conferences is that you have to invert your hypothesis at every parameter in parameter space, and does not appear computation feasible if you go beyond one dimension. So no one is actually doing this. So most, if not all, frequency confidence sets, I would say, rely on large sample theory. So if you do undergrad stats, you assume normal base, whatever conferences, or that your LRT statistics approximate chi-square distributed. It's actually only in high energy physics, and this is why I started this 5 years ago, that there's all this people actually thinking about Neumann confidence, which I never thought about, of actually inverting the test. And can you do this? Like, it's not computationally feasible. And how would you check the diagnostics without doing the Monte Carlo samples? There's like papers of that I read, which is how we started doing this, right? And now the thing is that our LF2I framework shows that you require neither large sample theory, because Neumann confidence does not assume your sample size is large. or you do not need Monte Carlo bootstrap samples at each fixed data. That's a computational hurdle. It's not possible to do on a fine grid. And it's nothing, it's actually just AI is just a tool. Okay, so here's sort of the secret ingredient, which is like when I presented this, people like, oh, it was actually Larry Bossman. I was like, how come nobody done that? I don't know. So it's just that I see it as, I love to, it's efficient construction of finite sample, even samples as one confidence sets. And the thing is that, well, you need to find those test statistics in different data, and people have that approximate the likelihood from your training set and posterior. I have slides for reviewing and giving credit to people. A lot of people do this. But the cutoff also depends on data if you want to be frequentist. The thing to realize, you don't need Monte Carlo bootstrap because you have your, if you have a labeled set of thetas and x's, the different quantities of interest you want, your test statistic or your critical region, they're all functions of theta, different, yes. But you can estimate them by what statisticians call regression. And then if you tell them CS person, they don't know what regression is, they just call prediction or whatever. But you have the tools for it. You just need, from your label set, you need to estimate these quantities, your whatever test statistic you have, and your critical region as a function of theta. And we can do it thanks to the advances in AI and machine learning. That's the bottom line. So you can get these C theta as a function of theta everywhere for very high dimensional spaces. So no Monte Carlo. Okay, so this is sort of a simple thing, and now we have software and everything, thanks to my amazing students that have been enduring all this. So we have like the labeled set, right? So the likelihood has to be true, and then price whatever, and we split it. So simulator is your simulator. That's what we started with. Or it can be nature now when we have cross-match catalogs. So split it, and then we have part of it. We learn the test statistic using whatever AI and machine learning method you want, and I'll talk more about it. And then we have another set, we split it or simulate or whatever. And I estimate critical values as a function of theta. And this is amortized. So once you train it, and I can estimate as a function of theta, then I can just evaluate for billions of millions of galaxies. Thanks to AI, it's like takes no time. Right?
When you say split it, you mean just split the data, right?
Well,
Or you split something else?
ideally, the way we explain is you simulate it. But then when we work with our
Simulated from that forward model.
yes, but when I work with my collaborators, they're not going to simulate for us, right? It's already pre-simulated, so we already have this and we split it, right? Same thing.
Got
But if you can simulate, it's better.
It's better,
But
got it.
yeah, but it's slow sometimes or whatever. So here's the thing. So the test statistic, we can estimate it from the labeled set as a function of theta. And once you've done it, it's amortized. I just evaluate it. I stick in the observed data. It's very complicated thanks to machine learning. I can have different SATA, different probe. It's a computation issue, right? It's not a theoretical issue, right? And then theta, I can just evaluate it for all, over my entire parameter space. It takes no time. Training takes time, and training is hard. And same thing, if I estimate critical value as a function of theta, then I can just evaluate. So it's amortized. Once you have trained these, then I can just evaluate. I can get my confidence set instantaneously. And if I do the critical value, well, they guaranteed to give you the right coverage. I mean, it's an old result from 100 years ago. And I can do the same thing, yeah.
So you do have to worry about sparsity in your D set, don't you?
Sparsity.
Yeah,
Simulating data.
when you're simulating.
Yeah, or similar or whatever.
But if you have very high dimensional space,
It's not a problem with AI, but the simulation, I started working in high energy physics. It's cheap, right? So they have 500,000. My data can be, I mean, if it's sparsity, it's a training issue, right? But I estimate my test statistic from
yeah,
it.
no, so what I'm thinking of is, suppose the example that I'm thinking of, David will be familiar with this, is atomic data sets. You got 10,000, 100,000 lines, each of which has its own parameters.
Yes.
And if you start, simulating from theta, and you can get any,
Yes.
Yes. You'll need billions and
Yes.
maybe trillions.
Yes. Yes. It depends on if it's sparse, you need more data. And I don't know. There's no. Okay, so So to get coverage, you just need to get that right. But to get power, you need a good test statistic, a good definition, and you need a good estimate.
So what ended up was like, you can have a little bit of data, you just get an enormous confidence.
Yes.
So in the standard valid coverage.
Yeah,
it's-
bad
yeah,
constraining
it's, you know,
power.
it's just
Yes.
useless,
Yes,
but, so,
Yes.
yeah, so there's
Yes.
there's no free lunch,
Yes.
right?
yes,
okay.
there's no free lunch. But if you have a good data, whatever, good prior, you get high constraining power. It's exactly what you said.
Yeah.
Yeah, there's no free lunch. But I think before we didn't even have the tools to do this. I think frequentist statistics was not useful.
This is very much like the older chi-square, except the modern version. Older chi-square
Except
just
there's no
eliminates
chi-square.
these parameters, doesn't fit the data.
Yeah.
Well,
Yeah,
but this is
there's
a
no-
lot fancier version of.
No, this is not fancy. It's just like 1930,
Yeah.
whatever. But it's we can do it, right?
Right.
So okay. So all right. So what test statistics should you use? So originally we were using a defined likelihood-based test. A lot of people worked on it. I mean, I have to give credit. They really inspired us. But now we're moving towards test statistic computed from posteriors, and Waldo is one of these, which I will explain. And the two reasons. One is I think a lot of my collaborators, they're really working on posteriors. There are a lot of tools, generative models, neurodensity estimators, so it's kind of easier to compute posterior than computing LRT, which has you have to find the max, your MLE. It's computational. We have these neural networks that do it. That's one reason. The second reason is LRT does not leverage prior information. I mean, it's just likelihood-based. The posterior, you can show that it actually benefit from good knowledge if you have good knowledge. So there's something more there that can give you.
But there's a price, right? But if the price is bad,
Yes,
it will give you
Yes.
tested with terrible. power.
yes, but
But if the price is good, it's fine.
yes. Well, but it will still give you validity.
I know, but validity is easy to get.
No, with the credible regions, you don't. There's no guarantee.
No, I'm saying with your method,
Yes.
because rejection
Yes.
method, obviously you by
Yes.
definition
Yes.
is getting.
Yes,
right.
yes, exactly. But we also have the independent tester diagnostics. So coverage is difficult because you don't know from credible region what it is, but we can test it independently. We can get the coverage plot. And power, you see anyways. You can see it's huge.
Yeah.
So you see
So,
that.
but there is a fundamental downside of what you're doing. Theoretically and practically that happens too. The Bayesian method is coherent in the following sense. If I have more information, my region will necessarily get smaller.
Yes,
Doing hypothesis testing, you could have more data, better data, the region actually gets dispersed because it's a reverse argument. The people have shown this thing. In
yeah,
the hypothesis things, they're not probability of the events. They're condition on the events happens
yeah.
to rejection. So you can have these situations where you get some more data, you end up with worse results, yes.
Maybe we can have. talk
Yeah,
about
that's
this.
that paper actually is by CMU colleagues, you know, in American statisticians.
CMU.
Yeah, what's his name?
Larry Weissman?
Mark Subridge. They have these
Okay.
papers in American statistician to show
Oh, okay.
the illogical part of the hypothesis. This has nothing to do with your what you're doing.
Let's talk about that in a minute.
Because that's-
Yeah, so I'm not, can I continue?
Yes.
Yeah, of course, when you want to.
Yes.
Oh, okay. Oh, I thought it was one. So, okay, so the test, this is one version, LF2I. So the test statistic we're using is called Waldo, or we call it Waldo, it was kind of a joke on the wall test statistic. So, yeah, so that was a joke, actually, it was a new guy that kept saying Wald, and I said, no, it's not Wald, and it was like, yeah, let's call it Waldo. And then it was like, oh, no, not bad, and I was stuck with it. So just to remind people, so Wald test statistic, if you want to test the theta zero, like in your parameter space, you basically compute the MLE, right, the maximum likelihood estimate, and you compute it with your null values, see how far they're away as sort of a goodness. Well, you can almost think of it as a conformity kind of score. So instead of using the MLE, we use the Bayesian version, which is the posterior mean. And we'll compare that to null, like how far is it? Does the data you see, do we think it comes from the theta zero with testing or not? So you can see the predicted value, how far is it from theta zero? as kind of test statistic. And the great thing is that when you use prediction methods, that's actually what you compute often if you minimize the L2 loss. And if you estimate the posterior, right, then we can also compute the mean. It's a computation. So well, basically that's that testing. For every theta zero we test, we compare the posterior mean with that value, and then we normalize with the posterior variance instead of the inverse of the Fisher.
There's actually a better one than this.
Yes,
I
probably.
better often. Do not use the posterior variance. Using the frequent variance of the posterior mean. That's give you better frequentist
Oh.
property.
Can we talk about
Yeah,
this?
because the posterior variance, it could be, it's off, right? Because the red, but
Yeah,
because you're worried about the frequentist property. Just take the
Yeah.
posterior mean as estimator, which incorporate prior informations. But you
Yeah.
look at the variance of the frequent variance of the posterior mean as estimator, standardized that way.
yeah, is that?
Now the computation might be hard.
Yeah, well, computation is important.
Yeah, computation might be hard.
But let's, I only need like a conformity score, and then I can use the name on. So it doesn't matter. I just want high power,
Yeah,
right?
I
So-
have
and we
punched
have
that
a-
might be better
yeah,
high power.
Yeah,
We can
so,
talk.
yeah. So here it's because the posterior variance is very easy to compute from the posterior.
Yeah, I
variance.
understand that.
Yeah, and also from a posterior, we can also compute it. And the thing is, it's amortized once for your train data, once you have that, your prediction and predicted variance, I can just evaluate it for whatever, right? And D, you can see because of neural networks, I can just put in different probes or different channels. It's an network design issue. There's no real, hurdle, like with classical regression methods. They're the same. It's just hard to work with that data. So that's why I say machine learning. Right? So once I have it, so that's our test statistics. So you learn that from one branch, and then I can evaluate very quickly. Okay, so now how about the critical value? So if you think about what it means, so this is like the sampling distribution test statistic, which I can evaluate for any kind of theta zero, any kind of data once I trained it. So basically, we want to find the cutoff where the tail probability is alpha, let's say 10%. So this critical value is really the alpha quantile, right? And here's the thing, I cannot just piggyback all the advances that's been done in machine learning AI. So I basically want to know what's the C where the tail probability is 1 minus alpha. So all I need to do is like, I can leverage the quantile regression methods to find the alpha quantile by basically regressing my test statistic, which I already learned, and it's amortized and evaluated on theta because the critical is different cutoff for different theta. And I can learn that from my second split of data or similar data. So that's all it is. And once you have that, as long as I talk about stat part, I'm fine. But at some point when I I need some values at some point, never mind. Okay, so now we learned this, it's amortized. Now I can get my confidence sets, and they're valid as long as my quantile regression is good. I mean, it's easy to show that regardless of the number of observations, and how well we estimate the test statistic and the choice of prior, that doesn't matter. As long as I do my quantile regression, I control the type 1 error. But as you know, if a bad test statistic, bad prior, or I didn't estimate tested it well, then constraining power is bad. But for validity, it's not the problem. And then this is actually useful. I won't go through the details, but the issue is that once you have a procedure, the point is, I can look at diagnostics by doing this other regression problem. I can actually estimate empirical coverage as a function of theta everywhere. It's just another regression problem. So even if you don't like this, you can check your credible region. I can check for different values of theta, what is actually your coverage. And I'll skip the examples, but it's useful for some when I check, like, should I marginalize of Newton parameter, should I profile, blah, blah, then we can see what regions in the parameter space you get your nominal coverage or not. So it has been very good diagnostic tool, which is independent from the construction. So I just want to make sure I go back to the problems. So we have the calorimetric view on energy measurement. So you have one, I want the momentum of the muon. I have these energy deposits, 50,000 cells. What should I do? Can I get confidence sets with, yeah, so the two questions. One is, well, we work with particle physicists and their frequency surveys, they actually want frequency conferences. Now I'm in an astronomer audience, so takes a little bit more convincing, right? Why you should care. But there were two questions they cared about our collaborators. One, can you get confidence sets with actually real, nominal coverage? So do you get valid uncertainties? That was one question. And the second is, should we build, this is similar, should we build a highly granular calorimeter? I mean, there's a cost involved in it. They actually, I don't know if they exist yet, or use this highly granular ones. And this was a stats talk where this is just picture of road transport of structure from the Atlas asteroid. I just put it there to remind statisticians that detector optimization is a real issue, because as stats people would just get data and forget where it comes from. And it's just like, there's cost. It's expensive to build a highly granular. There's a lot of people working on it, so it's not like you just have that, right? So the second question is the added value, do we get higher constraining power instead of just having one calorimeter that measures the total energy? So the two questions. And okay, so we just did the simulated data and we took it, and from this highly granular simulations, we'll create nested data sets. So one is, let's say I only measure the total energy sum, right? So just like, I just average, I just sum all the energy in all these cells. The other is we have hand design features that our collaborator designed before we started working with them that they thought were meaningful. And the other is full calorimetric data of 50,000. And these are three different data sets. And for those, we predicted the mean, the posterior mean, and the variance, and then we formed our test statistic. We sort of frequentize the posterior information using the confidence set, using our construction. Then we'll compute the confidence sets. And here you can see the coverage diagnostics. So basically, you form our confidence sets, and then we'll see what is the coverage as a function of the, in this case, the parameter space is one for different energies. So we actually use just Monte Carlo simulations, because in one dimension we can do, so tomographic binning basically. And then we can see, is the actual coverage right? So we don't need our branch. And what you look at here is, so this is the prediction sets you form, 68, that is historical reason they want 68% confidence sets, because they're one sigma, right? And the prediction sets, the coverage is very wrong at high energies, which is actually where we're interested in using these calorimeter at very high energies. And these are our electronic confidence set, and from the posterior, we form these Lehman confidence sets. And regardless of what the input is, we get, not surprisingly, we get the right coverage for our energies. And the second question is validity, yes, we get it, and it's local for every single value in your parameter space. And we can check it with tomographic binning, because it's just one dimension here. And how about constraining power? So is the valuable information high granularity, calorimeter? So constraining power, we cannot look at the size of our confidence set, or the average size. Actually, I think we look at the median interval here, the median length, and as a function of energy. So smaller is better. And the blue shows you, if you just use one slab, this is the constraining, well, kind of constraining power. What is the median interval length? But if I use a higher granular, I get higher constraining power. Of course, part of it is numerically, maybe we could do even better, but at least that's what we can do. And we also, just for reference, we put in the prediction sets. They're not valid, but it's just to show that, it's actually smaller. Wait, it's as good as, what is the prediction set? Yeah, it's actually better than the prediction sets with the whole 50,000. Okay, so let's go to the other example of this, and then I have some on the stall also. So this is the example. I showed credible reagents for neural posteriors. They do not actually, they look small, but they actually don't you know, only 30% of the time, this is frequency, do you capture the true value? So I think that's not a good thing. And here we just frequentize the posterior. So we use the same, we didn't train the neural networks. We just use the same neural network that the CNN, and then we form a Waldo test statistic, and we use the Neumann inversion. And these are the confidence sets we get. They're a little bit bigger, but I think they should. So the bottom line, which is cut off, is these are the credible regions, and these are the frequentized from normalizing flow. They're overconfident when the prior is here, the truth is here, it's misspecified. They're small, but they're not really, you know, I don't think we can say that we are 90% confident that this would include the true value. So they're smaller than I think they should be for when you look at constraint power. So if I use the same posterior, same CNN, whatever, this is what we get. So if your prior is well specified, there's not really a difference between two conferences and credible region in this example. But if they sort of mismatch with the truth, the credible region looks better than they should be, and here they look larger, but I think they should be larger because the info was not very good. And Shirley said if it's really bad, then yeah.
So there's
And this is diagnostics, you see it.
there's a more theoretical question, because I already see that your region's not necessarily convex,
Yes.
right? That's one, but do you have some results to at least guarantee they're connected?
No,
That-
they're
that-
not
that-
connected.
they're not
Another
connected, okay.
person does not.
There could be confidence.
Yes.
Like all over the
Yes,
place.
yes,
Okay.
but so we have independent check that, and this has nothing with the construction, we check the empirical coverage of functional data. So we can see, even with your Bayesian, if you don't like our method, we can say that, okay, for these regions, the parameters, if the truth was here, your regions will not give you the right coverage, and it can be really bad, it can be zero, as they show for some stalls, real data. And we can see that we get the right coverage everywhere, and this is independent check. From that held out set, or if you can simulate even better. And then I think constraint power you can see anyways. So I don't need
Are
to.
they, I mean, do you actually in your simulations, because the one thing you'll be worried about, I understand the
Yes,
validity is not an
yes.
issue because you construct that one.
Yes,
Competition is great. The question then is that if you have a problem where you have lots of, high dimension, lots of nuisance parameters,
yes.
you don't have enough information,
Sure.
do you actually get the simulation show that region is not even bounded?
Not even bad. Well, I see that I can check that it's a problem.
Okay.
Nuisance power is very hot.
You say,
That-
of course.
I ignore it here.
Yeah.
But we are working, I have some papers on that too. That's very interesting.
But just theoretically, I guess this hypothesis testing method does not really guarantee
No.
the region is finite. It could be like a one top
Well,
line.
it's worse than that.
It's what-
That's not, I mean, the main issue with nuisance parameter, to get validity, you have to control the type 1 error for all parameters, including.
all
yes,
nuisance, yeah.
so it's actually hard to even get validity because of the issue. And this is why people use like approximate method, like profiling or whatever, because the nuisance parameter is really a nuisance.
You can say that's what it- but-
Because I can't even get this.
Right, so what I'm gonna
So
ask you
not
is
even-
that can you actually treat the nuisance parameter as if of interest?
Yes.
Construct a joint confidence. for all
Yes,
of
that's
these.
what you do, but it's very hard.
But then it's a lot more computation.
It's, it's
There's not enough information to read the chain.
I mean, it's very hard, listen, because it depends on what scale you're talking about. Sometimes 100,000, right?
It's gonna be hard.
So this is hard to get even control type 1 error because of numerical stability issues.
Yeah.
So
Right.
when we're looking at this kind of approximate schemes and the no theoretical guarantees for real problems, that if you profile, you would actually, yeah, we can discuss. I don't-
Profile is still asymptotic.
this is still hard, but we're working on it because I think it's important.
But news is actually where now you're really trying to be based, trying to put down some price, even you don't believe them. Trying to integrate some of the things just to
Yeah.
control it.
Well, yeah,
Okay.
I mean,
It's a
it's difficult.
bad situation.
It's difficult. I
difficult.
mean, we're trying to find test statistic that's kind of insensitive to
Mhm.
that, is like pivotal, or-
Pivotal,
yeah, that's what people
Yeah.
do. But it's, I kind of tend to lose constraining power, so I can show these nice
Yeah.
They're just too big.
Too big,
Like,
yeah.
yeah. I mean, it's a practical, it's both theoretical hard, but it's very much numerical also.
Yeah.
Right, so here's the thing, and we can guarantee coverage everywhere if the price, even if the price pool is specified, but you have higher price if you have tighter constraints. So here's maybe I kind of done the main thing. Here's a new direction that I'm very excited about, because most people think of LFI as simulation-based inference. But your simulator could be nature, right? I mean, so here, this is a new project where for the property of stars in the Milky Way from low resolution spectra from Gaia using cross-match catalogs. So part of it, the stars have more precise labels from cross-matching with high-res spectra from Apogee. And so you have like the train set that's labeled with theta and x. So these are inferred data from a different probe like Apogee. So we assume that they're reliable. I mean, that's another issue we're working on. So as I see it, it's from the likelihood, the data and process, which is nature plus instrument effects of that. And prior is whatever we see in the set. And we want to infer for new data. We assume that the likelihood is the same. So this is the first experiment. Okay, so this is just Josh and the credits are gone, and Alex LaRoche. They made a plot. It's about 500,000 stars from the Gaia satellites. Gaia has like millions that have been cross-matched with high-res from Apogee. And x-axis, this is Q x-axis with temperature, effective temperature. I'll collaborate say that we need to flip the axis. So let's see, hotter is this way, and colder, redder is that way, and the gravitational constant decrease here. Here are the main sequence stars. Our sun should be 5,000 K. And eventually, when our sun is out of hydrogen, it's converted to helium, it will take this last phase on the giant red expand and become a red giant. And these lines are, you can think of the evolution tracks with fixed metallicity, and this is in dex. So the sun should be 0 dex, orange, somewhere here. Okay, so that's a key diagram. And my next, did I say no? So I have no cheat notes. So, okay, so the observables, the low resolution spectra from Gaia. Don't ask you what exactly the resolution is. There's probably someone in the room that knows, because we're working with the BP spectra, which is the sort of transformed coefficients. And we want to infer the stellar labels, parameters, gravitational constant, metallicity, effective surface temperature. And we have cross-match data with Gaia with the Apogee catalog. And the subset, I think it's, well, we have 500,000 that are cross-match, but Josh and Alex identified about 200,000 of them as having good labels. So basically, I think they cut off all the ones that have large measurement errors, everything with a flag, bad, they're gone. And we left with 200,000 with the good labels, right? So that's what we worked on for the first test of ideas. And okay, so these are preliminary results, and I have it's not published, but I have some of the results. I put them in here. So these are diagnostics, and I just want to show that if you form credible regions, and there's no shift here, so the same distribution for the train and target. So if there's no shift, then I think the Bayesian credible regions on average actually has frequency coverage, but not a fixed data. So the typical undercover where the price is low, right? So I just wanted to show this so we can see the diagnostics. So most of the data for the Gaia is here. Actually, there's more in the giant for some reason than main sequence data. And we actually undercover credible regions. I think it's 90% credible region in the low density regions. And we can see that we have diagnostics, which I think is pretty cool. And here we just frequentize it, and then the coverage is correct. And these or just example, I wanted to see the credible region conference set stored somewhere, just to make sure that looks good, because as you say, they could be huge, just getting good coverage is not enough. So we pick them along these metallicity lines. So all I do here is that I show is we apply since we can't do Monte Carlo tomographic binning, and also, hey, you can simulate, this is real data, right? So we just did the coverage analysis, which is basically a regression to estimate the coverage of your formed conference and credible region. And that's how we got it. Okay, so here's the thing. So maybe this is not so impressive. So the first setting is just what I showed you, and we have the examples of 12 different stars where we actually computed, and I'll show you one example. And this is the coverage diagnostic for HPD sets of credible regions, and this is the LFQ ISIS, so coverage is good. So then I said, well, we already know this, that if the prior is misspecified, we get bad results. So, and all astronomers know that the distribution of your stars may not reflect the truth, right? You don't see everything. If it's far away, you don't see it. So then I just like, I told my student that why don't you like kind of like change your train set? So and it's cut off. So so we made a setting which is giant dominated. So we train on the giants, 98% of the giant, and we make inference of the main sequence stars. So there's a distributional shift, and you can imagine you might have the stars still exist, but maybe I don't see them. So let's say I only see the giants, and I want to infer on main sequence stars. And if I compute my credible regions and look at my density, and use my procedure and look at where the maximum is, and I should look at the coverage of it and can get the coverage. The coverage is actually 0. Out of these, none of them include the true values. But we can frequentize it and get the 90% with the same output. And I can play the other game, which is maybe more interesting to you guys, that I train on the main sequence 80%, and then I make inferences of 20. I want uncertainties. And if I form my credible regions, then it's 0% coverage. None of them include the truth. But I can use the same output and frequentize it, and I get the coverage. And I'll show you, we'll have 12 examples. So this is like estimate coverage. One is train and target is the same. You don't get actual coverage, but I think people might not be so interested if it's like 70%, 80% for the credible set. But anyways, we can correct that. And if it's like skewed because selection bias or whatever, and it's giant dominate, your coverage is like kind of like down to 0% on the median. We can correct for that with the same output. And I can play the other game with main sequence. So exactly what they are is because of the numbers, because we're not simulating, it's just that we just have these stars, right? We can't do anything. So you can't compare them this way. And here's some examples. I have 4 times 3, so 12 what we looked at. And this is a star that was kind of close to the sun, so I say sun-like star. And this is when there's no parabolic shift. So it's the same. I split our set on train and target, so that's from the same distribution. I didn't do anything.
Sorry, can I ask a quick
Sure.
question? What is it you're predicting? I mean, what is the theta?
The properties of the star. So in this case, it's the gravitational constant from the spectra. I can't see the axis.
Temperature.
Effective temperature and metallicity. But I can do more, but that's this, it's the surface level. Yeah. I mean, and I only have I have one spectra, and then I want to, for that star, I want to get it, and I have 200,000 stars. And I didn't simulate it, so we have limited data, right? And I can do whatever I want, right? And these shows you the credible regions. There's no shift. So the coverage we can check is 70. It's actually not 90%, but I don't think people are so worried about it. And this is when we frequentize it. It's 90%, which is what we want. But I think maybe people are not, it's not enough for you to do the frequency method. But here's interesting. So here I shift it. So I trained on, I split this. I said only 2% comes from the main sequence. 98% is from the red giant. But my collaborator said the other examples may be more interesting. And you can see that the credible region, first you don't have diagnostics, where diagnostics we can see, right? In the other plot, the coverage. So it's all black, it's 0% coverage. And you can see one example, this is where the sun is, and we don't know, there's no way you can know. And this is my credible region, they're always off, like 0% coverage, like all this, none of them actually includes the truth, right? In my whole set. So, and I can frequentize it. Now the coverage is actually is frequency covered 90%, and this is maybe what you want it to look like. It have for that specific realization, it kind of includes it. It's larger, but I think it should be large because you have full constraining power if your kind of prior over here. We can see if you're the same, a good prior, then it's small. But if it's bad prior, I think it should be large, right? So we have coverage and they're larger. And this is kind of just the bottom line. And I think I made a half hour of validity, LF2R for inverse problems. It's important. If a prediction problem, how do tools? But it's the inverse problem that's hard. So the data and process, I think, is the truth. It's the truth plus measurement error. So validity diagnostics, so credible regions from, it doesn't matter what tools you use for neurodata system, does not necessarily reflect with the true parameters because of, priors being mismatched. But with LF2I, and we can frequentize posteriors to construct locally valid confidence sets for finite number of observations, just need one observation, and then run diagnostics. Power is a big thing, but you can see your power anyways. You can see if your balcony the large coverage is hard to see without diagnostics. And this is basically how all the code out. I think it's pretty good. I want astronomers to put a software engineer on it and build it in your pipeline, but so this is software my group has worked on. It's completely modular. Your test statistic, a lot of people compute the really good test statistic. You can plug it in. We can do the normal construction. Or if you don't like it, you can just use the coverage diagnostics and look at it, see if you're credible region. I mean, I've talked to data scientists that don't want to do this, but they might want to check the, actually, maybe they're interested and see what the frequency coverage is. So you can do that. And, it's very simple. So this has prior independence by construction. You get nominal coverage regardless of prior, as long as you do your quantile regression well. But if you have well-specified prior, I think there's a lot of theoretical, research that could be done. You can get higher power. And we have simple results from that, which is from, really from the 1900s. So what's next? Some open problems. This is Ashley is not here, but it's her and Josh's slide. We want to incorporate uncertainties and bias. So many data sets that have heteroscedastic and sort of missing data, bias subsets with the ground truth labels available. So I think we solved the bias problem, but not the uncertainty problem, because we assume that we just threw away all the data where we think the train and target is not right. And I mean, the first astronomy application I worked on was photometric estimation. And I know that, the measurement errors are not the same for close galaxies and far away galaxies. So right now we just throw away everything so they're the same, right? So we want to work, maybe we can, first we want a simulator to check what we're doing, what are labels for simulations. That's one thing. We can work with spectroscope photometric data. And the other is an extension what we're doing now, right? We want partial label data. So right now, we're working here, we say the measurement errors are the same. We basically just discarded everything when measurement errors are too large. We want to extend that since astronomers actually have an estimate of the measurement errors. It's a very hard decomposition problem, but we want to extend that to the whole catalog of labeled data with the measure, when you have an estimate of the measurement errors and do this. And eventually, of course, we want to work on the whole survey. So these are very general methods. It's not necessarily Gaia or anything. So I think this is it. And sorry, I used up the whole time.
Perfect.
Yeah, so there's the collaborators and the credit to NSF that got cut off, but, you know.
All right, so if there are any quick questions from the peanut gallery, we should get that now.
From Zoom.
From the
Yeah.
Zoom, yes. Yes, sorry, there's also the peanut gallery. Yeah. And if not, I'm going to turn off the Zoom. How are you all doing?
So who else is on the Zoom?
Let's see.
Yeah.
There are lots of people on the Zoom.
Yeah, we have Zoom.
Yeah, I saw Alex. Not.
Right, so thank you all for joining. So like I said, I'm going to turn off the Zoom now. There's this. And I suppose you can always talk to Anne. I mean, at least.
Oh, yeah,
here.
definitely.
Yeah.
So go ahead.
Please.
Yeah, thanks for the talk. So I have actually two questions. So for one, for a practicality. So I mean, in particle physics, for example, we often do the contour regions and we do a lot of these like kind of data analysis hacks to actually make sure that where we apply the inference in the end is like not too much out of domain as what we train on. And
Okay.
we have very like, I mean, we have very good tools. Like, how do you see this like related to this, to your work? Like, I mean, we can basically make sure, or like, we gain a lot of information already about the price from like how we construct the contour regions and all of this. Like, how does it relate to your work basically? Because you show that it's mostly relevant, like your priors, like for the test and the training are very different, or they're like not matching. Like,
No, yeah, I mean, are you a party?
yeah,
An astral party?
no, part of
Oh.
it.
But for collider experiments, as I understand it, they don't really, I mean, they do Neumann construction, but I think they use like large sample theory a lot. Right, so they assume Wilkes theorem, they assume chi-square distributed, they don't actually, so that's one thing. But I don't know what data you look at, but for collider experiments, they're often in the high large sample region. So I think they're sort of fine with that. And the people I talk to, they're not really work with prior, but maybe it's in that, like, I mean, most of the time people work in Atlas or CMS. So I don't think people were interested in priors. So it's more just like it's a Neumann construction, but using Wilkes theorem for many experiments. So I don't exactly. So your question, like how to use it for?
Yeah, or like what could be like a benefit of?
Yeah, so I think the benefit for the examples
this
I
kind of
see,
following.
but I don't know if it will be interesting particle physicists, is that many scientists that I've been working on, they don't believe in, they think frequentist methods only work when you have large sample sizes. So that is the number one motivation I did this. So maybe that's the short answer.
So
Yeah.
basically when we are in this like very high. like,
Yeah,
it's
basically, can you even do frequentist methods in practice when your sample size is 1? That I think is the main thing. Yeah, but in the collider experiments, at least the people I've talked to, they might not be, it depends on what experiments you do, right? They actually often assume large sample, they think it's not bad. I don't know, so it might be different. But if you work in astroparticle physics, like the gamma, not talking the X-ray, the gamma ray showers, that's a few photon counts, and that is a little bit different from in the collider experiments. And it's also like different because you have atmospheric effects. Like I started working on this on simulations for high energy physics where the simulator is very good, right? So not like in astrophysics, so the model is very good. And then I kind of started looking at other problems. And I think right now I'm very excited about the sample size 1 thing, because when I talk to my colleagues, they kind of think, oh, it doesn't mean it's latent. But no, not necessarily. Still a parameter. It's just that I only have 1 measurement, right? So that I think is number 1. And the other is like, well, of course you get the prior probability for free because you frequent these. So that's, I can advertise that, but that you can say that by MLE too. It doesn't have this issue, right? But now that I'm interested in the 7 new things, and I I have a very small group, and that is like, can you leverage the prior information, right? Can you benefit from it? Like sample size one, I think, and prior probability, that comes from free, right? We have them. The other is like, you know, can you leverage good prior getting high constraining power? And also what Shelby said, what about news parameter? Those are $1 million questions, right? I haven't solved any of them. And yeah, that's interesting. And the measurement errors, as I understand that's a real thing, right? Assuming that you have your likelihood model maybe works in the collider, but it's not true for astronomy, right? It's not the same train and target. Yeah, so I don't know if I think there's just a lot, this is a very general method, but the real problems look very different in different areas.
And then, I don't know, if I may, like, just a quick follow-up question. I don't know if you're familiar with Kai Grammer's work of this, like, period-free inference, where we directly regress the likelihood from particle physics. And I was wondering, like, also there, like, I mean, because you mentioned in a, like, quick in the introduction, that mostly what you see for actually approximating the likelihood is a kind of, like, prediction. But for example, in his method, he's directly regressing the true underlying likelihood. And what do you think about this?
Oh, I mean, I can't talk particularly about his work, but there's a lot of work on estimate likelihood posterior. If you want confidence sets, I don't know, you could, it's not trivial still to form like valid confidence sets just because you have the likelihood. So you could use your estimated likelihood.
Okay.
I mean, that's how it started. Estimate likelihood is kind of hard. Well, estimating likelihood ratios is hard because you have to do an optimization problem. We just lost so much power from that. So you could, so as I think of it, but it takes some convincing and people like, you know, talking to people. I think of this as a general framework. I would love if people could collaborate with us because I mean, I have a couple of students. So if people are interested, so you can use it, like if there are a better way, you can estimate this. If you're interested in confidence sets, you can use that because it's modular, right? You see what I'm saying? So I think it's great. You can use a posterior, you can use likelihood ratio. So I'm not working on that specifically, but I think of it as, I mean, I would love if people could collaborate with us. Yes.
So one big group you may want to collaborate if you don't know them yet is Regina Liu's group.
Yes.
Minko, because they've been doing confidence distribution.
Yes.
Which is just changed
Yes.
right? To more.
Yes.
And, Regina, I don't know if you were at the JSM.
Yes, yes, but there were so many people that
Right.
I didn't talk to.
But she was talking about
Yes.
the individualized prediction using the.
Yes,
Yeah.
she talked about getting not the median, the
Right.
in the graph,
Yeah, in the
yeah,
graph,
but,
because that's-
the cent, whatever.
The data depths.
Yes, exactly. Yeah, hold up, she was the keynote speaker,
Right,
so I
right,
didn't.
right.
Yes, I mean, I gave this talk in maybe
Okay.
select the inference, but it was a different version, maybe
I see.
many years ago. He was my discussant.
She was discussing.
Yeah, but I haven't, they in Rutgers, I
Yeah,
haven't.
they've been doing a lot more,
Yes.
they're just doing it, but
Yes.
then, like, they also have this thing, what they call a prediction. It's very much on confidence interval using this random
Yes.
seeds idea. It's
The
much more close to
retro
the,
sampling.
yeah, right, it's
Yeah.
much more close to the fiduciary inference.
Yes.
Yeah.
Well,
It's essentially just trying to get the thing, get the
yeah,
right coverage, yeah.
I mean, is it Ming, is that right?
First of all, thanks a lot for the talk. I come across this term of likelihood-free inference quite a few times. I think it's the first time I really felt like I could understand and follow. Thank you so much.
Yeah,
I
well,
was
thanks.
particularly the intuition with the intractability,
Yes.
the latent variables that
Yes.
really helped. Because as a
Yeah.
Bayesian, I can relate to
Right.
intractable things. So this was really nice. I think I could follow the construction via the name and inversion, but what I here's a question. How does in the Waldo test statistic, if you compute the posterior quantities
Yes.
with different, you said it depends, the coverage doesn't, but the power depends
Yes.
on the prior.
Well, yeah, so
But
kind of,
you're using neural networks to estimate.
yeah, yes,
So
yes,
I was wondering how the approximation method, because for neural networks.
yes.
can't just do MCMCs in some cases, right? It's quite expensive, so.
Yeah, so let's see, this is a technical question. So the issue of validity, like the coverage, and I think that's solved as long as you find where to cut it off, right, the tail. So that's
Yeah.
it, right? So power depends on, as I see, two things. One is how you define your test statistic. Like some test statistic, maybe order like you say, the likelihood ratio test is uniform most powerful for the whatever. So that's a theoretical, how should you define it? But then there's an additional question where I'll lose a lot of power, and that's a numeric issue. Like if you don't estimate, so I define it this way, theoretically should be really good, like maybe the LRT, but then I can't solve the optimization. Yeah, so there are two things. So one is like, as I see it, the definition of it, and that's a theoretical question, and it's very hard for general problem. The other is like the estimation, and I want to do both. So I choose Waldo because it's easy to estimate. So the optimal one that I don't show you is actually to have the posterior, just take posterior, evaluate it. That gives me optimal power. But in practice, I found that if you have a newer downside estimate, the posterior is not very good estimate. So I suffer a lot from constraining power in the end because of numerical instabilities. So the reason I use Waldo is it's very robust, because even if your posterior is not very good estimated in different regions, I just compute the average. And yeah, so it's, I don't know if it's answered you, but I think every time
So you say the average of what?
your posterior. So the Waldo takes the posterior mean, so your posterior takes,
Maximum or posterior?
and no, maximum posterior is the mode.
Oh, okay.
Average, right? So if you do a prediction method, right? If you minimize the L2, you get the conditional mean.
Yeah.
Yes, that's what I'm using conditional mean. Because even taking the max of posterior, it's a little bit harder. So I'm looking for, I mean, I haven't worked on it. I worked on it for a while, but I mean, my group is, you know, I can count them with my fingers. It's just like this
Okay.
numerically, this is very robust. Like,
Okay, but I get,
yeah.
but I get that the location of the posterior doesn't depend that much on the quality of your overall approximation.
Yeah.
But I would assume that the variance does.
Yeah, the variance is, I mean, since I calibrate, theoretically, it doesn't matter if I divide. I mean, I talked to Larry, he said why? But we see it really matters because I stabilize it. It's like if I have a test that has normal distributed, if I calibrate, it doesn't matter theoretically. But if I divide it with its variance, then I have a standard normal, right? And it's just easier. The results will come out better because of numeric issues. So we divide with the variance just to, I think it just stabilizes things.
Mhm.
But theoretically, it doesn't matter because I'm a tester. If I know that, you see, so a lot of it's very hard. Like to get something to work for real data is just incredibly hard. Theoretically, I mean, there's the theory question, but then it's like, what actually can we compute fast and what's robust? So that's, in the end, we're going back to Waldo because it just seems very stable. It doesn't give you the best constraining power, but it seems pretty stable because I compute summary statistic. I do the mean, how different it is. It's pretty stable. And I divide with the variance, which is pretty.
Well, certainly it's increasing numerical stability.
Yes, exactly.
But there are times will matter, but that's a more complicated, right?
Yeah.
If you standardize about theoretical variance
Yes.
itself would depend on theta, then that would change the game.
Well, the variance does depend on.
No, not the posterior variance, doesn't depend on theta, only depend on data, which does not matter, just.
Yeah, yes, it's different in different regions.
Right,
Yes.
but if the variance standardization itself depends on the parameter you're testing, then it will be actually a different test. It will create different regions.
Well, I compute my test statistic and yeah.
Right, I mean, think
Yes,
about the Bernoulli.
yes.
See, but if the
Yeah.
variance is p times 1 minus
Oh,
p,
I don't,
then
yeah,
that would be a different story.
yeah, I mean, one big difference from what I do with Minga is that most of my, what I do is, continuous random variables. I don't do discrete data, so.
No, but that's fine, like single Poisson. If you
Well,
model,
so I said-
well, but what I'm saying, what's important is the parameter itself,
Yeah,
right? The parameter
Yeah.
itself, whether that's, is the parameter goes into the variance as well. If you standardize something, the parameters in the variance,
Yeah.
then it will change your test statistic.
yes,
It's a long equivalent.
yes, I mean, this is general method, and there's a lot of work on what test statistic for your problem, right? And this is just one example, we use the Bayes factor, or one paper, likelihood ratio test, whatever. I mean, this is just general, and then the critical value, yeah, so different problems would be different testing, but this is sort of the general framework and plus software, I guess. So that's how I see it.
Okay, all right.
Yeah.
Thank you,
Now
thank
on
you.
to 5.
Yeah.